Hello, guys. Welcome back to MedZone African Motives. We are still on our electrotechnology N3, working with the measuring instruments. So, in this case, I want us to consider actually the major part of our calculations as we are working with our measuring instruments. We are going to need to focus. There are questions that will be given on the calculations. So, that is the major part that we are going to focus on. What is it that you need to understand on these measuring instruments? All right, so there is a measuring instrument referred to when you have got a connection of a shunt resistor. So we are going to have this connection of a shunt resistor. All right, let's say we have got this shunt. What is it? What is the connection that we are talking about? A shunt connection, a parallel connection. So this is the connection that you're gonna have on when a shunt resistor is considered. You'll be having that is the meter in this case. That is our meter. That's our galvanometer. Then we're gonna obtain in parallel with the resistor, which is connected in parallel. That is to make it a shunt connected in what? In parallel. So let's say there's a current flowing into and also out. So remember from your Kirchhoff's law that the current that is flowing into the junction will be equal to the current flowing away from this junction. And which currents are we talking about? One, we have got this current that is flowing into the meter, which is our galvanometer. So across this, that is our meter in this case. We have got the resistance across the meter, and we are also going to obtain the current flowing across the meter, which is this IM. So this is the current across the meter that is affecting this side. So as we can take a closer look, once there's a resistance and a current, meaning to say there is going to be a voltage drop across this meter also. On the shunt field resistor, on this shunt connected resistor that we have, we are going to have the current flowing across, which is the shunt current to the shunt resistance. So definitely a current and a resistance will give us a voltage across. So we're going to have the voltage across the shunt, which is the same as this is a parallel combination. What about this current? This becomes our load current, which is the current supplying these two. So the shunt and this meter current, the current that is flowing across the meter is the same. See, guys, this thing of working with DC machines, a lot of time you think always you're with DC machines. So that is the shunt and the current of the meter, which is this galvanometer there. So these are the two things to be considered. So you can make anything the subject, you can make shunt the subject, the one for the meter, the subject, it's up to you. So when you're talking about the current, the meter is connected parallel to the shunt resistor. In this, the meter and the shunt resistor are connected in parallel. Okay, that is the major part. The meter is connected. So you're simply referring to the meter is connected in what? In parallel to the shunt resistor. To the shunt resistor. So as we can take a closer look, we are talking about the shunt resistor. So at the end, we need to know how to calculate that shunt resistor, which is the major part of our connection that we are having there, to say what is going to be the value of the shunt resistance that we are given. So when dealing with shunt resistors, or when you're having a shunt resistor, we can consider this as an ammeter shunt. Okay, so when they give you this as an ammeter shunt, you think of what? A shunt resistor connected, like what I was referring to before. So let's take a closer look into the calculations that can be made. Like I said, we need to calculate the value of this shunt resistance, and in parallel, the two voltages will be equal. Remember, in parallel, the voltage is the same. So the voltage across the shunt is equal to the voltage across the meter. And the voltage across the shunt is the product of the currents, the current of the shunt and the resistor of the shunt. The voltage across the meter, the product of the current across the meter to the resistance across the meter. So we can calculate our shunt resistance by dividing by this shunt current. So in this case, we are going to obtain the shunt resistance to this formula, which is simply representing, if we take a closer look on this formula, this whole part here, I am the current of the meter, and the resistance of the meter is the voltage across the meter that you're given. So if you are given the voltage across the meter, there is no need for you to use this. You can just use this as voltage across the meter over the current, over the shunt current. That is provided you are given this voltage, but in most cases, they won't give you like that. They will give you these resistances and the currents. So the shunt current can be calculated because you might not be given that. So for you to calculate the shunt current, that is the formula here. Remember, from this Kirchhoff's law, we can obtain our shunt current. Just simply subtract this meter current from the load current. So we are going to obtain the shunt current. So at the end, we can say the shunt current is equal to the current across the load minus the current across the meter. So meaning to say, whenever you are not given the shunt current, and there is a load, which is the current that the maximum load current. This is actually referred to as the maximum, that is the maximum load current. The maximum load current. So you might be given anything, then you consider your Kirchhoff's laws, this and that. That is how you're going to have the shunt resistance at the end. So that's an ammeter shunt where you calculate the shunt resistor. All right, then there's another circuit, which is the series multiplier, or when you're talking of the voltage multiplier. All right, so this is considered to be a voltage multiplier. So a voltage multiplier is the one that you're considering as a series multiplier. So the moment you consider that the other one is shunt, the other one is series, it can be better that way, okay? The other one is shunt, the other one is series. That part can help, but the series is the one that you consider as the what? As the voltage multiplier. The shunt is the current shunt, which is the ammeter shunt you're considering when you're dealing with the ammeter, the current there. You're working with current, that's the ammeter. There you're gonna focus voltage multiplier, series multiplier. So it's a connection that is simply in a series. So we're gonna have something of this nature. So that is gonna be, okay, this is too much. Let's just see here, something like this. Then we have got the resistance of the series in series. Remember, this is series connected to the meter, which is, in this case, it is no longer in parallel. Remember, the last part, they were parallel. This time, the resistance and the meter will be in series. So that is our meter in this case. Remember, the part of the meter, guys, I talked about this, that on the meter, you expect to have the resistance of the meter in this case, and also the current that is flowing across the meter. Here we expect to have the resistance of the multiplier, which is the series, that is in series. And we also expect to have the current of the series, but this is a series connection. So these two will be equal. The series current will be equal to the meter current, the current across the meter in this case. In series, we do understand that the voltage is because we're going to have a voltage here, which is the voltage across the series, the voltage across the meter, related to the supply voltage. This will be the sum in series. So in terms of the voltages, the voltage, that is the supply in this case, which is the maximum voltage that you can be given, will be equal to the sum of these two, the series and the one of the meter. So, but remember that, because at the end we need to calculate the series resistance. There we say these two are the same. So meaning to say it's simply, instead of us having the voltage drop across the series field, it was supposed to be the current across the series field times the resistance of the series. But this is also equivalent to the meter current that you're given. So you can write it in terms of IM, which is the meter current. So meaning to say, in this case, we are going to have the product of the meter current to the series field plus the series resistance, sorry. Then we consider, in this case, the voltage across the meter, which is the current across the meter to the resistance across the meter. That is it there. So in this case, we can calculate the series, or we can have the formula for this series that we are given, which is our series resistance in that case. All right. So what is going to be our series resistance? Let us take this to the other side. It's going to subtract. That's V minus IM Rm is equal to IM RSE. So that is, we need the series. So we're going to divide by IM. So you can divide everything by IM like this. It's up to you. Or you can divide every term separately. Here, you divide by IM. Here, you divide by IM. It's up to you. So if you do it this way, this will cancel. And also here, because we have got IM, it will cancel to this IM. So at the end, we are remaining with the series resistance equal to V over, so it's going to be the voltage there from our supply. Remember, we've got the voltage from the supply over the meter current that you're given minus Rm, which is the resistance of the meter. So we can manipulate this formula into this. That is up to you. Or you can simply, like I said before, divide everything by IM, just leave it like that. So it's up to you. You can use this, or you can apply with the previous formula. And like I said, in this connection that we are having, considering the currents, that is the same. The series current and that of the meter is the same. So you have to consider these two things into application. All right, so you're going to have another part again in our syllabus that they need us to consider, which is also important as part of our syllabus, which is the 2 wattmeter method for 3-phase supplies. All right, there is what we refer to as the 2 wattmeter method. All right, so there is a 2 wattmeter method. A 2 wattmeter method for 3-phase. So this is for 3-phase supplies. It affects the 3-phase supplies. Okay. So for a 2 wattmeter method, you are going to have the connection of 2 wattmeters as you are given. So you're going to have something like this. So remember your wattmeter. So just gonna have our coils here representing the part of the wattmeter. So these are coils that you are presenting. All right. So that is gonna be our wattmeter 1. So this is our first wattmeter connected. So you're gonna have this other connection of another wattmeter in this case. So here gonna have another wattmeter again. Okay, just something like this. So guys, just make sure you work out your revisions, question papers. Also do revise as much as you can, work with question papers, understand the concept of the topic that you're given and how do they ask these typical questions. All right, so there we've got the wattmeter 1 and the wattmeter 2. This must be to the ground here. So that is going to have live 1, 2, and 3. And that is going to have our neutral. Remember, this is a 3-phase. So what happens is that with the wattmeter method, you can calculate the power, total power. So there is a power connection. There is a power calculated here, sorry. There is a power also calculated here on wattmeter, on each wattmeter that you are given. So it follows that the total power is simply the power that is across wattmeter 1. So it's just like P1. So let's just write as P1 plus P2. That is the power across the wattmeter 1 plus the power across the wattmeter 2. So here you'll be given the power, and here you're going to be given the power. You add those two. That is the total power, just like that. So with this, we can answer as many questions as we can. I want you to go through each and every part that you're given there. On question number 9, a measuring instrument, that is the one that you're given, has an internal resistance of 15 ohms and gives, take note, it gives a full-scale deflection at a current. So that is the major part. It is measuring current. You're talking of the ammeter shunt current. It gives a full scale of, the current that is being measured as the maximum. That is the one that you are given there, which is going to be at the meter. It gives full scale. Sorry for that. The full scale is on the meter, like on that measuring instrument that you're given. Then calculate the resistance required to enable the instrument to be used as a voltmeter. So there is the major part of to be used as a voltmeter, reading 0 to 12 as a voltmeter, meaning to say this is supposed to be a series multiplier, not a shunt, but a series multiplier as a voltmeter. So this full scale deflection current is, okay, let me explain this way. That is the current that you are measuring across, that is across the meter, like the one that is given from this one that you to be supplied, the one that is being supplied. All right, so you're supposed to be careful in that case. Remember, this connection that we are referring to across the meter is the same. So when you are considering a voltmeter, it will be the same. Okay, let me have our diagram back, guys. Remember, we had that diagram of a series. So let me explain it with the diagram so that you understand me here, because I'll end up losing you here on this one. I want you to understand what I'm trying to say here. Remember, that is our meter here in series with our resistance. So that is what they're trying to say here. I just want you to understand this. Okay. The measuring, which is our measuring instrument, has got an internal resistance. So the resistance of the meter, this one, this is the measuring. Okay. The resistance across the meter is 15 ohms. And gives a full scale deflection at a current, meaning to say the current that is supplied there, which is in series, this current is the same. So we are given also the current across the meter at full scale deflection of 60 milliamps. calculate the resistance required to enable to measure the as a voltmeter. That is where we say it as a voltmeter. We're going to have this as a series. So we need the resistance of the series for this to be a voltmeter, having a reading of 0 to 12. And like I said, the voltage will be the maximum voltage. So this, you're going to take the maximum voltage from 0 to 12. We use the maximum voltage there. So that's it. A voltmeter, you are considering a series. You are considering a series, in this case, this one. We are back to this part of our voltage multiplier. A series multiplier. That is where we are. So with this, the question is asking us to calculate that resistance. So we saw that, guys. I'm not going to talk about these formulas. We manipulated this our formula. So we saw that this series resistance, in this case, sorry for that, the series resistance is going to be given by the formula V over IM, the meter, minus the resistance of the meter. So in this case, we can calculate the series resistance, which is this one, from the voltage that we are given, 12 over the current across the meter, which is 60 times 10 to the exponent of -3, minus the resistance across the meter, which is 15 ohms. So by simplifying this, you are obtaining that resistance that will make this to be a voltmeter. And that was going to be 185 ohms. Just like that. So questions can be just like that. So understand the question, how it is given. Just have a diagram, then the formulas. I talked about this. Explain mutual inductance as applicable to a single phase transformer. It is not necessary to make a sketch as part of explanation. All right, so this is part of your transformers. Like we are asked to explain the part of the mutual induction. What is it that you're going to consider when dealing with the transformers? So this is the major part of our mutual induction. Two coils are brought together. That is, in this case, we are given that these two coils are brought together, namely the primary input, which is the input, and the secondary windings, which is the output. The supply is connected to the input windings. The voltage forms a magnetic field between the primary and secondary windings, and the variation of the magnetic field induces an EMF of mutual inductance into the secondary winding. And there is no electrical connection between the coils, only magnetic connection. There is no electric connection, but only magnetic connection to be considered. Then on 9.3, state two advantages of a damping mechanism when working with a damping mechanism. What is it that you have to consider as the advantages? It is very accurate. It is almost of a uniform scale, and it prevents pointer from oscillating. It is well shielded from any stray magnetic fields. These are the most important to be considered. So we're just going to consider also this section as well. Let us check another part on question 9. The 2-wattmeter method was used to measure the power drawn by a 3-phase induction. So we talked about the 2-wattmeter method, guys. Power, you simply add the given power. Remember, one is going to measure another power, and another one is going to measure another power. And that power is simply the sum of the two that you are given. So in this case, you are asked to calculate or to determine the total power drawn by this motor that you are given. So this is simply the sum of the two, that is 14 kilowatt plus the other one is taken as negative 6,8. So you add negative 6,8 to 14. That is going to be a minus at the end. So that will be 7,2 kilowatts. Remember, these were in kilowatts. So that is it there. Then on 9.2, you are given the ammeter connected to the secondary side of a current transformer gives full-scale deflection 15 amps of 5 amps flows through it. Give the reason why the current transformer must be earthed during operation. Okay, so this is not even about. Okay, so what is it to consider? So this is to ensure the immediate discharge of any harmful energy to the ground. So that is the major part that you're going to consider, to ensure the immediate discharge of any harmful energy to the ground. State 2 safety precautions to observe before removing ammeter from high current measurement. What is it that you are supposed to consider? You can switch off the supply, that is through the primary. So switch off the supply, switch off the supply, that is in this case, which is current through the primary. Okay, so you do this through the primary. Then short circuit the secondary winding by means of short circuit. So also you must short circuit. All right, short circuit the secondary, short circuit the secondary windings by means of what? So this is gonna be by means of the short circuit. So it's gonna be by the means of the short circuit switch, the short circuit switch provided by the manufacturer, provided by the manufacturer. Okay, so that is what you're going to consider in that case. 2 marks for that. The 9.3, you are given a moving coil instrument with an internal resistance gives a full-scale deflection of this. Okay, so this is simply the resistance on the meter and the current on the meter. That is what you're given. I talked about that for to have any confusion. But the question was to calculate the value of the shunt resistor to be used with the meter so that this will enable to measure current up to 7. The shunt, you're considering the shunt connection in this case. And the other one, a series. So we've got 2 things there, a shunt and a series. So remember, back to our shunt here, what we had on our shunt. So do not forget that. So everything gonna consider on the shunt connection. All right, let me just remove this one in between that is affecting us here. All right, so there you're gonna consider what you have on the shunt. That is the first part. So there are 2 things to consider. 9.31, it must be considered as a shunt. So if you are to draw your diagram, guys, this one, it's up to you. You can just have a simple diagram just to show, guys, you do also understand what you're doing in exam. Do not just answer the question. Yes, you might be given the formulas, which is fine. I know that you'll be having these formulas, but just also try to sketch and see what's happening there. So this is it, guys. On the meter here, this is our meter. We have got the resistance of the meter, in this case, 95 ohms, and also the current at full scale deflection, which is 12.5 milliamps at the meter. So we asked you to calculate the value of the shunt resistor, which is this one. We do not know this, so that it will be able to measure a current up. It will be able to take a current from here, the supply of 7.5 amps. So we are given the supply current of 7.5 amps. What we need is the current across the shunt. We do not have that one of the current across the shunt. Remember from our formulas, the resistance across the shunt can be calculated, the current across the meter times the resistance across the meter over that, but we do not have the current. We do not have, okay, let's consider this. We need to calculate that. All right, so let me just write our formula down in this case so that you can understand. Remember, our R shunt is equal to the current across the meter to the resistance across the meter over the current across the shunt, which is we do not have this. So we can calculate this, as I said, from the Kirchhoff's law. We ended up having the shunt current equal to the load minus the current across the meter. So we can calculate the shunt current from the current across the load, which is the current that it can now measure minus the full scale deflection across the meter. So that is it, guys, 7,5. So we're going to have 7,5 minus the current across the meter, which is 12,5 times 10 to the exponent of negative 3. This is in millimeters times 10 to the exponent of negative 3. So that was going to give us 7,4875, something like that in amps, which is the shunt current. With this current, we can calculate the shunt resistance from meter current, that is 12,5 times 10 to the exponent of negative 3. The resistance across the meter, that is 95, over the current across the shunt, which is 7,48. So it's going to be 7,4875. So that was going to give us the resistance of the shunt, which was going to be 0,159 ohms. So as you can see, the resistance across the shunt is very small. When you're calculating for the multiplier, is going to be bigger value that you consider. So that was 9.31. Also, with the same information, they want us to use this to calculate on 9.32 when this is now considered to be a series resistor, to calculate the value of the series resistor so that the meter can be used as a voltmeter, which is the same as the previous question that we just did when dealing with a voltmeter. Guys, I talked about this. I'm not going to waste much time. Remember, to be used as a voltmeter, that's a series connection that you are given. So in this case, it has to measure voltage up to 70, which is the maximum voltage to be measured here. Whereas this information that of a moving coil instrument does not change about this instrument, the resistance of the meter does not change. It's still the 95 ohms that we are given at a full scale deflection current of 12,5 milliamps. So we need this resistance of the series. So remember, we also talked about this multiplier circuit, a series. In a series, you can consider the voltage across the series, the resistance across the series from this formula. So I'm not going to talk about the manipulation, guys. We talked about all this manipulation. I just need the formula here. So we saw that this resistance across the series is going to be given by the formula, which is V over the current across the meter minus the resistance across the meter. And in this case, we do have everything. Voltage is there, maximum voltage to be measured, the current across the meter, which is that full scale deflection of 12,5 milliamps. That's 12,5 times 10 to the exponent of negative 3 minus the resistance across the meter, which is 95. So that was going to give us the series resistance of 5,505 ohms. Like I said, in series, the resistance will be very big. So this is 5,505 kilo ohms, very big. So that is how you can work your questions on the measuring instruments. You need to understand what you are given on the circuit. Okay, the information, what are you working with? Are you working with a shunt where you are calculating the resistance of the shunt connected resistor to the meter that you are given, which is giving a full scale deflection current? Are you calculating the series resistance when this meter is to be used as a voltage multiplier to measure a certain voltage, which is a maximum voltage to be considered. That is the maximum voltage to be considered. So if you're given from 0 to 12, maximum is 12. To measure voltage is up to 50, up to 50 volt, up to. This is the limit. It cannot exceed this, up to that. That is the maximum. So you consider the maximum voltage on the voltmeter when this is to be considered as a voltmeter. If it is to be considered as a shunt resistor where you calculate, this current will be the maximum, which is the maximum load current. That is the maximum that you have. So these are the major part. Can we go through our formulas, understand these formulas, what is happening, and also on a 2 wattmeter method where you can calculate the total power from the 2 wattmeters that you are given. So these are the typical exam questions that you're going to need in your calculations. Let's work with more questions as we are moving on. But for now, guys, that's it from MedZone African Motives. Till